Have you ever wondered how chemists manage to take a complex, totally invisible chemical mixture and perfectly separate it out? I mean, it sounds kind of like magic, right? But it's not. It's actually this incredibly precise science of physical and chemical manipulation. Welcome to This Explainer. I am so thrilled to have you here. Today, we're diving deep into the absolute unsung hero of chemical analysis, the stationary phase. In the world of chromatography, this is the invisible terrain that makes separating microscopic molecules possible. We're going to unpack exactly how this works, pulling straight from our source material to demystify the whole process. So, here's our roadmap for today. We'll start with the chemical obstacle course, move on to physical parameters like pores and particles, master polarity, modify the silica matrix, look at cellulose and mineral ligands, and finally, wrap up with why the rate phase matters. Section 1. The chemical obstacle course. Let's navigate this microscopic landscape. I want you to think of chromatography as this intricate racetrack, but designed specifically for molecules. You've got two main players here. First, the mobile phase, that's a liquid or gas that sweeps your sample along. And then you have our main focus for today, the stationary phase. This is the fixed material, usually a solid or a liquid layer, that literally slows down the components of the sample. So the molecules that strongly adhere to the stationary phase, well, they get swept along way less rapidly than the ones that don't. And it's exactly this difference in stickiness that separates the molecules out in space or time. Section 2. Physical parameters, pores and particles. Time to evaluate the physical terrain. Picking a stationary phase isn't just some random guess. It involves evaluating several really specific physicochemical parameters. Chemists have to look at the size of the particles, their specific surface area, the volume of the microscopic pores, and the overall distribution of particle diameters. All these factors come together to define the baseline properties of the stationary phase. It totally dictates how much room these molecules have to move around and interact. To really wrap your head around the scale here, let's look at nano-thin layer chromatography, or nano-TLC. In this super precise setup, the particles making up the stationary phase are roughly 4 micrometers in diameter, and the pores inside them, just 6 nanometers. We are dealing with an unbelievably tiny, incredibly precise physical obstacle course. Section 3. Chemical terrain, mastering polarity. Because really, it's all about the chemistry. Now, physical shape is honestly just half the battle. We also have to think about the chemical friction these molecules experience. A lot of the time, the go-to foundational material is silica gel. Silica gel is a polar material, and how it behaves is largely driven by the molecular groups on its surface. Specifically, we're talking about the ratio between silanols and siloxane groups. The big takeaway here is that this specific ratio determines the hydrophilic, or water-loving character of the phase. The more silanol groups you have, the more polar and interactive that surface becomes with certain compounds. And that brings us to a massive concept in chromatography: normal versus reversed phase. Bare silica, that's a normal phase. It's hydrophilic and polar. So using a polar mobile phase will actually favor the migration of polar compounds. But chemists can also create a reversed phase. Imagine taking those silica gel particles and coating them in non-polar paraffin. Suddenly, this reversed phase is lipophilic, meaning it loves fat, and it's non-polar. The craziest part? This generates completely opposite elution orders compared to normal phases. It literally flips the script. Section 4. Modifying the silica matrix to customize the track. So, how do chemists actually build these custom tracks? Covalent bonding. They can bind various chains directly to the silanol groups right on the silica surface. If they bind simple alkyl chains, things like RP8, RP18, which just refer to carbon chains of different lengths, they create that non-polar reversed phase we just talked about. But they can also bind organic functional groups like nitriles, amines, or alcohols to create customized polar phases. They are literally attaching custom molecular hooks to the track so it works with any type of mobile phase. Let's think about a real-world example from our source text to see this in action. Imagine a test sample containing 3 different steroids, each with a unique polarity. We've got methyltestosterone, an alcohol with low polarity, cortexolone, a diol sitting right in the middle with medium polarity, and hydrocortisone, a triol, which is highly polar. Now imagine racing them across 6 different stationary phases. The results of a test like this are honestly mind-blowing. When you run this separation on a normal phase, using bare silica, the highly polar hydrocortisone basically hits a brick wall. It barely moves. Meanwhile, the low-polarity methyltestosterone zooms right past and moves the fastest. But then, When you switch to a reversed phase using those custom-bonded alkyl chains, the entire order completely reverses. The response factor and the migration order undergo a dramatic reversal. Just by chemically modifying that stationary phase, chemists have entirely flipped the behavior of these complex steroids. Section 5. Cellulose and mineral ligands. Let's look at specialized supports for unique compounds. While silica is super versatile, it's definitely not the only option out there. Chemically modified cellulose supports, either as fibers or crystalline powder, are used all the time in thin layer chromatography. The most famous one is DAE cellulose. This is a basic phase packed with diethylaminoethyl groups. The hydrophilic character of polar phases like this gives them awesome ion exchange properties, which makes them absolutely perfect for separating specific things like amphiolites. And then you have mineral ligands, which are essentially types of plaster. Now, why on earth would you use plaster? Well, it deliberately makes the stationary phase fragile. If a chemist actually wants to get the pure compounds back after separating them, this is exactly how they do it. They run the separation, physically scrape or break away the specific zones of plaster that have the compound they want, and then just extract it using a solvent. The phase is intentionally designed to be destroyed so you can recover your prize. Section 6. The right phase matters. Let's tie this all together. To wrap up our journey into the microscopic world, I think our source text says it best. The choice of a stationary phase involves the evaluation of several factors and physicochemical parameters. Pulling off a successful separation isn't just luck. It's a highly deliberate, calculated choice of particle size, pore volume, and incredibly precise molecular surface engineering. The stationary phase really is the invisible engine running the whole show. So I'll leave you with this thought. We just saw how simply tweaking a microscopic molecular chain on a surface can completely reverse the physical outcome of a chemical test. If we have the power to manipulate matter at this level, to untangle the most complex invisible mixtures, what other invisible landscapes are out there, just waiting to be engineered? Thank you so much for joining me on this explainer, and keep questioning the microscopic world around you.